Okay, so our next speaker is Brian Lemon from Boston College, to talk about positivity of your classes.
Great. So first of all, let me thank the organizers for the chance to speak. I am very glad to be here. It's fun to be here. So the work that I'll be talking about today, partly it'll be joint with Mihai Fulger, who's a postdoc at Princeton. He's here. Part of it will be joint with Jen Xiao, who's a student of MIT. Okay. So here's the setup. Throughout the talk.
And you know this board doesn't move.
Yes. The reason people are writing too small is because the boards are too small. I'm going to get through this talk, and not once will you protest it. Well, I guess I already lost. So, anyways, moving on. So here's the setup. Throughout the talk, X is going to be a smooth projective variety over the complex numbers, and also throughout the talk, n is going to denote the dimension of x. So I'm not going to keep writing n equals the dimension of x. N is always the dimension of x. The starting point for us is going to be the Riemann-Roch problem. So very old and well-known problem in algebraic geometry. So given a divisor, L, on x, the problem is to find the dimension of the space of sections of the corresponding line. Okay, so remember that a rational map between projective varieties is given by the sections of a line. So if you like, you can think of this as maybe a first step in understanding the category of projective varieties. And because of that, it's very hard. But even better, from a modern perspective, what you'd really like to do is you'd like to find the dimension of the space of sections of m times L for all positive integers m. And this is an important idea, that the best way to capture the geometry of a divisor is to work with the entire section ring and not just the sections of elements. Okay. So we've taken a hard problem and we've made it a little bit harder. But the advantage of this perspective, we shouldn't really view this as a loss, but as an opportunity. The advantage of this perspective is that now we can study the asymptotic behavior of these spaces. Maybe we don't need an exact answer, but we can say something about what happens in the limit as n grows. So this is leading us to the following principle. I'm going to attribute this principle to Zariski. I don't know if that's exactly fair, but with Zariski, it's probably reasonably safe. So here's the principle. The asymptotic growth of these dimensions, the things that we're looking for, as m increases, is controlled by intersection theorem. So this is a pretty ambitious principle, right? Intersection theory is something that we can actually do. It has more of a topological feel to it. Whereas the dimensions of these spaces, these are very hard to determine in general. They're very subtle. It's more sort of a holomorphic field. And so relationships like this are pretty rare in algebraic geometry. So it's an interesting idea that you might actually be able to make progress using perspective. Okay, so let's try to make this a little bit more precise. If we want to understand the asymptotic growth of these spaces, the first question is, what rate do they grow at? So let me just record this as a fact. There exists a constant, C, which of course depends on the variety x and the divisor L, such that the dimension of the space of sections of ML is less than this constant times n to the n. So these spaces are growing in sort of a polynomial rate, and the polynomial is bounded by n to the dimension of x. Okay. Also implicit is not just that this is true, but that this is somehow the best you can do. So really the rate we should be looking for is n to the n. So this is leading us to the following definition. How can we now quantify the rate of growth? Well, we're going to define the volume of a divisor L. So it's denoted by vol of L, and it's defined to be the lim sup as n goes to infinity of the dimension of h0 of xml divided by n to the n over n factorial. So what is this doing? This is essentially identifying the optimal constant c that one can put here. Right? And this is a very natural invariant, capturing the growth of these spaces. This term n factorial is just a rescaling factor to make the resulting numbers look more like integers. Okay, so this is the definition of the volume. I actually wanted to spend a little bit of time on the properties of the volume function, in case you haven't seen it before, because it's not immediately clear how this is useful for this principle is risky. So let me write a few properties down on the board. First of all, if you have an ample divisor A, then the volume of A is just a top self-intersection number. Okay, so this isn't too hard to see, right? If you have an ample divisor, then the hierarchical homology is vanishing after a certain point. And so you can actually calculate H0 on the nose using Herzberg-Riemann law. And if you do that, this is the calculation that comes out. Okay, so already we see Zariski's principle in action. Another fact which we'll need, and which maybe is pretty reasonable, is that the volume is homogeneous. So if you have a non-negative integer c, if you rescale, sorry, this should be for an arbitrary divisor. No, not just for n. So if you rescale a divisor by a positive integer c, the volume rescales by that constant to the nth power. The volume is invariant under numerical equivalence. So this fact is maybe a little bit more surprising. So that is, if you have two divisors whose intersections against every curve are exactly the same, then these divisors have the same volume. So in other words, the volume function descends to numerical equivalence classes. It's really a function of numerical equivalence classes, and not just for divisors. So by combining these two, we can naturally define the volume for any Q divisor class. Right? If you have a Q divisor, then some multiple of it is an integer class, and you can just sort of compute the volume using this rule. So now this is heading more in the direction that sort of I want to go in. It turns out that the volume extends to a C1 function, a differentiable function, on the Néron-Severi space tensor R. So we've seen that it naturally defines a function on the Q points in here. And it turns out that this function extends continuously, and in fact differentiably, over the whole space. Okay. Then there's one more important property of the volume that we'll need, which is that if you look at this volume of the sum of two divisors, it satisfies an inequality like this. This is for L and D effectively. So this is saying that the volume is log concave as a function on the Néron-Severi space. Okay, this isn't, when you think of log concave, this isn't naturally the expression you think of, but you can rearrange it to look more like the familiar definition of log concave. Okay. So we started with this sort of, with this invariant defined via asymptotic geometry, and we came up with a function on the on the numerical space, which has some interesting analysis associated. Okay, and this is sort of Zariski's principle in action. You could relate sort of the analytic features of this function to the interesting asymptotic behavior.
Sorry, I'm surprised that this function is C1. Just on P1.
Piecewise.
No, it's C1.
Just on P1, isn't it 0 if you're negative and x if you're positive?
No, it's 0, and then it's the degree. Piecewise C1, yes. Piecewise C1, yes, thank you. This should be on the pseudofactor.
But it's also continuous, not piecewise continuous.
It's continuous everywhere, differentiable on the pseudofactor code. Yes. Good, thank you. Good. It's great when people call you out on false things that you said.
So it's C1 on the actual effective.
On the interior. Okay, great.
Is there higher degree differentiability in?
That's false. Yeah, C1 is the best you can. Okay, so the question that I'd like to answer, or the question that motivating question for the talk, is does Zariski's principle hold for other kinds of cycles? So the geometry of cycles is much harder than the geometry of divisors, right? There's a lot that we just do not know about cycles of higher codimension, but nevertheless, recent work over the past few years suggests that maybe there's some analog to Zariski's principle in more generality. Today, I'm just going to focus on the case of curves. Curves is a situation which we understand best, and so I feel like we can give the most complete picture for curves, but ultimately we'd like to understand it in more general. Okay. So let me discuss applications briefly for those of you who are not birational geometers. There's two areas of applications which are sort of obvious. Right? The volume is used all the time in birational geometry. It's really ubiquitous. It's maybe the most important invariant of a line bundle. So similarly, if we can answer this question for other kinds of cycles, we hope that it would also play an important role. Another, maybe less obvious connection is with cycle theory. Right? If you want to find the existence of cycles satisfying certain geometry, this is related to questions like the Hodge conjecture, Bloch's conjecture. So the connection's not immediate, but there's some interesting work of Voisin showing that there are actually some connections between these classical conjectures and this sort of positivity theory that I'll be talking about. Some other connection points, which I do want to put on the board. One is with convex geometry. So if you have a toric variety, the questions about divisors and their volume, these can be translated to the world of convex bodies, so polytopes, understanding their mixed volumes. Geometric inequalities on the polytope side tend to have analogs for divisors. But it's much better than that. This isn't just for toric varieties. Via Okounkov bodies and similar constructions, there's actually sort of very deep ties between the two fields. And this has been fruitful in lots of circumstances. I'd expect that, similarly, this question should have ties to the toric world and the tropical world. It should lead to some interesting combinatorics if we get the right perspective on it. Another sort of connection that we'll see today is connections with enumerative geometry. So naturally arising out of this question, there's lots of maybe new and very difficult but very interesting enumerative geometry questions. It's giving us sort of a different perspective or a different class of questions, which I think is really interesting. So hopefully you'll be interested by it too. The last connection which I wanted to point out is with number theory. So the volume has some interesting analogs in Arakelov theory. It's also used in sort of Diophantine problems. And I think that if we really understand this sort of picture for cycles or for curves, it might lead to interesting analogs, sort of geometric analogs in these other situations. So this is an area which I think sort of touches on a lot of different kinds of mathematics and is worth pursuing. So let me start by fixing some notation. These are sort of non-standard, so I just want to get them all up on the board. So first, by n upper 1, this will denote the space of R divisors up to numerical equivalence. So it's numerals of very group of X, tensored up to R. By n lower 1, I'll mean the dual space. So this is curves up to numerical equivalence, M2 of R. So it's R curves up to intersection against our K divisors. Then by F upper 1, I'll mean the pseudo-effective cone of divisors. That is, you take the closure in n upper 1 of the classes of the cone generated by classes of effective divisors. Divisors. By F lower 1, I'll mean the pseudo-effective cone of curves. So it's the analogous thing for curves. And then we'll also need their dual cones. So Nef upper 1 denotes the Nef cone of divisors, which is the dual of the pseudo-effective cone of curves. So by work of Kleiman, we know that this is the same as the closure of the ample cone. And the Nef cone of curves is the dual of the pseudo-effective cone of divisors. Yeah, okay. Here the geometry is described by the sort of well-known paper of Buxom-Demy, Howard Petternet. That's maybe the geometric. Great. So remember, we're interested in Zariski's principle. We want to relate somehow numerical kind of calculations, intersection theory, to the actual geometry of cycles, the asymptotic geometry. So today, I'm going to start by talking about numerical positivity. Understanding numerically what it means for a curve class to be positive. And we'll do this via a volume function for curves. So here's the definition. This is due to my co-author, Xiao. This is his idea. So for a class alpha in the pseudo-effective cone of curves, we define its volume. So for curves, I'm going to denote volume with a hat. This is going to remind us that it's for curves and it's not for divisors. Okay, so just to keep the notation different. So we're going to define the volume of a curve to be the infimum over all ample divisors A of alpha dot A divided by the volume of A to the 1 over n, and then this whole quantity raised to the n over n minus 1. Okay, let's parse this for a second. So what is this doing? We're taking alpha and we're measuring how big it is against ample divisors. Right? That's the essence of this definition. Of course, if we rescale this divisor out A, then this is sort of going up. So we need to divide by something which accounts for rescaling. And the choice we're going to pick is the volume to the 1 over n power, which is linear in the rescaling array by what we talked about. Okay, so this is somehow canceling out the rescaling. And then we raise it to this power, which you should view as some sort of Holder conjugate. Okay. Yeah. So this is a definition. Let's see an example, which will help us understand what this definition means. So let's suppose for the moment that H and A are both ample divisors. And let me remind you of the Khovansky-Tessier inequalities.
Using the word remind in
Let me tell you the Khovansky-Tessier inequalities. So what these say is that if you look at this intersection, h to the n minus 1 intersected against A, this is at least the volume of h to the n minus 1 over n times the volume of A to the 1 over n. So this is some analog of the Brun-Minkowski inequality for divisors. That's the right way to think about it. Okay. So if you stare at this for a little bit, it's a very easy calculation. Maybe you can just do it in your head right now. You have to divide by one side to the other. So if you apply this to the volume function, we see that the volume of an n minus first power of an ample divisor is equal to h to the n. Okay. So in this special case, what is this function doing? It's picking out the root, right? This infimum is actually realized by, for h to the n minus 1, this infimum is realized by h, and then the volume is h to the n. So that's explaining why you have this exponent here. It's one way of thinking of it. Okay, so it's essentially sort of a root construction for classes of this form. So what's really going on here? So this, it took us a little bit of time to get to this picture, but this is the right way to think about it. This volume function is the polar transform of the volume function for divisors restricted to the net. So polar transform is a construction from convex analysis. This is an example of a convex analytic transform. And how should you think about this? Well, this is the analog in our setting of the well-known Legendre-Fenchel transform for convex functions. We're working with a cone, and our functions are concave and not convex, which is why it looks a little bit different. But it's really the analog of the Legendre transform. So so this is coming from abstract convex analysis, and let me inform you of what the Legendre-Fenchel transform does. So remember, it relates the differentiability of a function to the strict, well, in our case, it will be concavity of its transform. Right, this is the goal of the Legendre-Fenchel transformation. It relates differentiability to strict log concavity versus just log concavity. And in this setup, the way that you capture the failure of strict log concavity is via a Zariski decomposition. So if you don't know what a Zariski decomposition is, don't worry about it. I'll define one in a second. But if you do, I'm claiming that this is a good, or maybe even the right perspective of Zariski decompositions. What they're meant to do, the Zariski decomposition for surfaces, and also the sigma decomposition of Nakayama, and all these analogs for divisors in higher dimensions, the goal is to capture the failure of strict log concavity of the volume function. Okay. So in our setting, because we're sort of in this abstract convex setup, we need to understand the failure of strict log concavity of this, I'm just erasing it, of the volume function here. So we'll do that via, again, we'll call it a Zariski decomposition by analog of the surface case. So let's let alpha be, now I'm going to insist that it lies in the interior of the pseudo-effective code. This is the right perspective for us. then a Zariski decomposition for alpha is an expression as follows. So we write alpha is equal to b to the n minus 1 plus gamma, where b is a big enough R divisor class. Gamma should be pseudo-effective. And b dot gamma should be equal to 0. Okay. So again, if you know about Zariski decompositions, this is sort of a word-for-word analog of Zariski's original construction. Right? It's phrased a little bit differently, but for big classes, it's really identical. So if you don't, let me explain what this is a little bit. So it's splitting up alpha into two pieces. So this part we can call the positive part. So this, a complete intersection of an ample divisor is positive in a very strong sense. So it's splitting up into a positive part, and all the positivity of alpha is supposed to be retained by this positive part. And then we have this other pseudo-effective piece breaking off, and somehow they're orthogonal in some sense. I mean, it's not literally orthogonal, but there's some sort of orthogonality of the two expressing the fact that all the positivity is residing here. Okay. So then the theorem is that every curved class in the interior of the pseudo-effective code of every variety admits a unique Zariski decomposition.
In the case of divisors, my recollection is that such theorem does not exist, or
For divisors, what I'm calling the Zariski decomposition, the analog should be the Sigma decomposition. So let's just focus on. I'll talk to you.
that's not known to be
No, so that I'm using Zariski decomposition in a different sense. Yeah, that's right. So but here the positive part, I mean, it is positive as you might want. So it's just a different thing. Yeah. Okay. So this theorem holds in much more generality, right? This is just abstract convex analysis. You can work over in the Kähler setting or over an arbitrary field, but let me just stick with this for now. So the point is that the Zariski decomposition and the volume are sort of they go hand in hand. They're exactly the right tools to go with one another. So in particular, lots of the theory of the volume function for divisors, such as understanding its derivative or the Morse inequality, all of these sort of geometric inequalities coming from, convex bodies, they have analogs for curves, which you can sort of transport over using this language. So in particular, this captures the failure of law concavity just as we wanted it to. So if we have two classes in the interior of one of these curves, then the volume of their sum to the n minus 1 over n is at least the volume of the sum of the volumes to the n minus 1 over n with equality if and only if the positive parts are proportional. So this is, this is the strict law concavity. This is how to sort of think about the strict versus the non. Okay. So let me do a couple examples to illustrate why I think this is, the right perspective.
How does the volume of alpha relate to the volume of
the volume of alpha is equal to the volume of b to the n minus 1. And the other part is,
So b to the n minus 1 captured.
that's right. That's exactly right. Okay. So let me do a couple examples. First, let's suppose that x is a hypertaylor variety. Okay, and then I'm going to let Q denote the Beauville-Bogomolov form on the space of curves. Right, normally we think of the Beauville-Bogomolov form on the space of divisors, but dually you can define it on the space of curves just as well. Then I claim that this is somehow, this language is exactly compatible with the Beauville-Bogomolov form. Somehow the right way to think of it. So for decomposition, alpha is equal to, we have the Zariski decomposition over there. Then first of all, if you look at Q of b to the n minus 1 with itself, the Q, the self-intersection of b to the n minus 1 under Q is exactly capturing the volume. And then there's an exponent, which I better get right. Yeah. Then the negative part of the Zariski decomposition under Q, its self-intersection is negative. So long as gamma is not equal to 0, of course. And then finally, this orthogonality of the two parts is truly orthogonality with respect to the Beauville-Bogomolov form. And question. Much more than this is true, right? For divisors, there's these results of Huybrechts and Buxom describing how volumes and the sigma decomposition is exactly compatible with the Beauville-Bogomolov form. Then all the analogs hold word for word for curves using this perspective.
What's the continuity properties of the map that sends alpha to b to the n minus 1?
It's continuous
Differentiable.
and differentiable, but not C2. Simple. So long as you're on the interior. Okay. Okay, so that's hyperkähler manifolds. Now let's talk about torque varieties. So let's suppose that X is a torque variety, and it's defined by a fan sigma. Okay, and now I'm going to set up this a little bit differently. Let's suppose that alpha is in the interior of the Neff cone of curves. So how can we think about alpha? It's a Minkowski weight, which is positive on all the rays of sigma. Right, that would be the way to describe this. Then there's a classical theorem of Minkowski, which to this data allows you to associate a polytope P alpha. And then the calculation of the volume turns out to be a mixed volume problem. So the volume of alpha is the infimum over Q. There should be a rescaling factor. Sorry, it's n factorial times the infimum over Q of the mixed volume of P alpha to the n minus 1 with Q divided by the volume of Q to the 1 over n, whole thing to the n over n minus 1. But now here, where Q has normal fan, refined by sigma. Okay, so it's a mixed volume problem, but instead of looking at sort of the classical way of doing this for polytopes is to allow Q to vary over all polytopes, and then P alpha would achieve this minimum. But here we're restricting the normal fan of Q. So we get a new kind of mixed volume problem, and this is one of the rare kinds that you can actually solve. Right? So using the Zariski decomposition, you can actually write down an algorithm of sorts to solve this problem. Having said that, this is absolutely the wrong way to think about torque varieties. I put it down because I don't know the right way. But there should be some really beautiful combinatorics underlying this volume function. Let me not speculate, but if you know about torque varieties and you have an idea, maybe you could let me know. I would love to hear about it. Okay. All right, so far we've been talking about this volume function, which we've defined purely numerically, sort of using abstract convex analysis. But remember, the point was to get at Zariski's principle. So now we need to understand the asymptotic geometry of a class. That's going to be the next topic. Let me talk about geometric positivity. Okay, and the approach that I'm going to do here was suggested by a paper by Debar, Ein, Lazarsfeld, and Voisin. So they made a couple conjectures which sort of led to this train of thought. So let me give a little bit of background first. Let's consider a linear series, L. Okay, so suppose that we take a divisor and we look at the linear series associated to this divisor. Then the divisors in L, the linear series, containing a fixed general point determine a codimension 1 hyperplane in this linear series. Right. So insisting that a divisor go through a point, that's a codimension 1 condition on a parameter space of divisors. Okay. So now if you insist that a hyperplane go through several general points, each time you're cutting down by a hyperplane, and because the points are general, these hyperplanes will be in general linear position. So if you sort of take this logic and induct downwards, you find that the dimension of the linear series is the same as the number of general points contained in an element of L. The maximal number of general points contained in an element of this linear series. So when we're thinking about generalizing the volume function, the first obstacle is trying to understand what do these spaces mean for cycles of higher codimension. Right, for divisors we have this great correspondence with line bundles, but for cycles we don't really have a correspondence with vector bundles. It just doesn't make sense to, it's just a very mysterious relationship. So a different way of interpreting the dimension of these spaces is via point counts, via enumerative geometry. Right? We can think of the dimension of this linear series as saying what is, suppose you fix B general points, is there a divisor in your linear series containing all B of them? And the maximum B for which that will work is exactly this. Okay, so the idea of Debar, Ein, Lazarsfeld, and Voisin is to take this, take this analogy seriously and try to use it to understand the geometric positivity of other cycles as well. So now let's talk about point counts for curves. So now let's ignore this left-hand side, and let's just think about this problem for curves. How many general points can be taken in the curve? So the heuristic, it's not obvious right away what to do, but let me just tell you what to do, or remind you what to do. So the heuristic is to look at complete intersections in projective space, where this dimension n is the same as the dimension of your variety. Okay. So first of all, let's suppose that we take a degree d divisor in projective space and ask how many points does a degree d divisor contain? Well, we already answered this question. The number of points, number of general points, it's going to be h0, which is about d to the n over n factorial. I don't care about the other terms so much. Okay? Now let's suppose that we take these and we intersect them. So if you intersect it n minus 1 times, you get a degree d to the n minus 1 curve. And the number of general points that this curve goes through, it's again d to the n over n factorial. Right? Each time you, when you're intersecting divisors, each time you're decreasing the dimension of your linear series by 1, but that's negligible compared to this, this overall size. So the sort of surprising thing that comes out of this is that for curves, the number of general points, at least in this very special setting, and via this sort of unjustified heuristic, should look like some constant times the degree of the curve. Let me give it a different name. The degree of the curve to the n over n minus 1. Right? If this is equal to m, then this is equal to m to the n over n. So it's a little bit weird to see a non-integer exponent showing up, but hopefully it's a familiar non-integer exponent, if you've been paying attention. Okay, so what this is indicating is that now, by exact analogy with the volume, we want to do something exactly analogous. We define the mobility of a curve class alpha, and now I'm going to insist that it lie in the Z lattice actually generated by curves. Right, I haven't talked about what you might do for a Q class or an R class yet, so let's just stick with curve classes. The mobility of a curve class alpha is defined the following way. The mobility of alpha is equal to the lim sup as n goes to infinity of the number of general points contained in curves of class M alpha divided by m to the n over n minus 1, and then we have a sort of unimportant rescaling factor to get it. Okay? And this is exact, again, we're doing sort of exactly the analogous definition. Let me point out, and again, this shouldn't be too surprising, that if you read that this is homogeneous of weight n over n minus 1. So again, this is for non-negative integers.
Somehow the mobility part b to the n minus 1 is inequality.
Well, we're getting there. Yeah. Okay. So now we have this sort of mysterious function, and let me tell you sort of what we know about it. So the theorem is that this mobility function extends to a continuous function on all of n1 of x. Okay, so this sort of volume function, which we've defined, actually sort of becomes a well-behaved analytic function on this vector space. And again, the theorem that I actually proved is in much more generality. It's, for arbitrary singularities, arbitrary algebraically closed field, but let's just stick with this. Okay. Then furthermore, sort of one of the most important properties of this function, mobility also admits a kind of Zariski decomposition. So this was proved in joint work with Mihai. I'm not going to write down what it is, but it has a very similar field for sort of capturing the strict law concavity of the function. It's not how we phrase it, but it's morally speaking, it's a similar idea.
So in part 1, you mean preserving this stretching pools, right? Otherwise, it's
That's right. I mean, it's naturally homogeneous, which defines all the Q classes, and then it extends to the R classes.
otherwise it's a one.
That's right.
And the function is zero outside the zero.
And the function is identical, right, it's exactly the same. The function is identically zero outside the pseudo-effective code, so this is somehow picking up. In fact, the main point is to prove that it's zero on the bound. That's sort of the hard part. Then you get sort of continuity. Okay, so hopefully the way I've set it up, this feels very natural. But this function is extremely difficult to work with. And this is a really hard kind of, we just don't have the same tools for cycles that we have for divisors. So let's do an example. Let's do the first example. So let's consider the example where x is equal to P3 and alpha is equal to the line class. Okay? Then how are we going to calculate the mobility? Well, this amounts to the following question. What is the minimal degree curve through B points, B general points, of P3? Right? That's exactly what this question is asking. We're asking how many general points are contained in the curves of a given degree. And the answer is unknown. It's unknown in lots of ways. It's unknown in sort of this weaker asymptotic sense that we need. And it's not just unknown by me. I've been asking people this question for 3 years, and nobody knows the answer. This is potentially a very hard question. But there's this really cool conjecture by Perrin governing this example. So Perrin worked with this question, and he computed out lots of small degrees, up to 70 or 80 or something. And this is the pattern that emerged out of this. The optimal curves, in some sense, which I'm not going to make precise, but the curves that maximize the number of points given their degree, are complete intersections. This is a fantastic conjecture, right? There's this whole zoo of curves on P3. But somehow this perspective seems to be picking out the nicest possible curves, the ones with the best possible behavior. I think this is my favorite question right now. This is just amazing. And if true, this would imply that the mobility of alpha is equal to 1. So we really have the right conjecture, the right restatement.
Just optimal in the asymptotic sense or literal sense or both?
Well, certainly, in these complete intersections are going to be sort of spaced out. So in between, there will be other things. But whenever you hit sort of a complete intersection curve of the right degree, it will be the optimal one, and they will also be optimal in the asymptotic sense.
Your definition of mobility, can you just use that for subvarieties of any dimension?
Yes. So yeah, I sort of referred to this earlier. You can use this for subvarieties of any dimension, and this theorem is still true. There's something else I wanted to say, but what was it? Well, I don't remember. Let's move on. So now I'm going to do a little bit of a bait and switch, unfortunately. So there's a related function known as the weighted mobility. So it's denoted by WMO. And this weighted mobility is very analogous to the mobility. The difference is that it counts singular points of curves with higher weights, in some sense. Okay, so I'm not, I don't want to sort of get into this right now. The definition takes a little bit of time. But the point is that singular points get counted with higher weights. So why would you do this? Well, this is better reflecting the geometry of the blow-up, right? If you blow up a singular point of a curve, it looks different than if you blow up a smooth point on the curve. And so this is reflecting the intersection theory better. So in particular, this is actually something that you can do. You can actually compute this using Seshadri theory. And the weighted mobility of an n minus first power of an ample divisor is equal to h to the n. And this is for Hm. Okay. So now we've set up these two functions. One's defined numerically, one's defined geometrically. And the natural question is, how can we compare these two functions? So that's going to be sort of the last topic. So this is joint with Jen again, but it's building, sort of the hard part was done with Mihai. The hard part, understanding the mobility function. So here's the theorem. So let's let alpha be a class in the pseudo-effective code. Then, first of all, the volume of alpha is equal to the weighted mobility of alpha. Second of all, well, because we can't compute the mobility, it's maybe too optimistic to hope for an equality. But you can get an inequality like this. So you know that the two functions are sort of bounded with respect to each other up to a constant. The third property, and I think this is somehow, I think these are all interesting, but in my mind this is somehow the most interesting and most compelling, is that the volume of alpha is equal to the mobility of alpha, assuming conjecture star. So what is conjecture star? Conjecture star simply says that for H ample, the mobility of H to the n minus 1 is the same as the self-intersection of H to the n. So we can't compute the mobility in a single circumstance, but assuming we could compute it for complete intersections, we could compute it all the time, and it would exactly match up with this one. So this is Zariski's principle verified, right? We're doing, this is some sort of abstract analysis done on these spaces. These are geometric invariants, and they match up perfectly, which I think is, I think this is sort of a really interesting outcome of all this.
So counting these, assuming the conjecture, counting these weights doesn't actually matter.
That's right. For curves, anyways. So what's the strategy? Well, the strategy is to compare Zariski decompositions. That's how this proof goes. And this is analogous to Zariski's original paper, right? How do you calculate the volume of a curved class on a surface? Well, you take its Zariski decomposition, and then it becomes an intersection number. So this is exactly the analogous picture for curves on arbitrary varieties. And again, I hope that this seems very natural to you, but this is very strange. I didn't, when I first started thinking about this question, I thought there was no way this could possibly be true. I'm still somewhat surprised by this. Yeah, so what is this doing? This is singling out complete intersections via enumerative geometry. It's saying that this beautiful conjecture of Perrin on P3, that really we should be making it for every variety and every curve class simultaneously. That, using this idea of Zariski decomposition, the mobility should always be computed by a complete intersection class. I mean, this is really weird. Let me just tell you an example without saying it. suppose you have two varieties connected by a flip or something. And suppose you look at a complete intersection of ample divisors, this curve class, which is sort of maximizing number of points on one of them. If you looked at the strict transform, right, they're not intersecting the exceptional locus, so if you looked at the strict transform, you'd think that they were also maximizing the points on the other one. But this is predicting that it's not true. It's saying that if you deform it so that a component lies in the exceptional locus, the part that's left over deforms more. This is weird. I still find this very surprising somehow. But this is what's coming out of this picture. Okay. So for the last 5 minutes, let me tell you a couple other consequences of this. So I mentioned some very general applications at the beginning. Let me mention some more specific applications to birational geometry. Some time is remaining. So first of all, so this is a theorem with Jen and myself. We're able, using this technology, to show that rays over irreducible curves which deform to cover X are dense in the Neff cone of curves. Okay, so you should be comparing this to the theorem of Buxom-Demy, Pound, and Petronel. So what do they show? They show that such curves, these are called moving curves, irreducible curves which deform to cover X. They tell you that the classes of such curves generate this cone. We're saying that the classes over such curves are dense in this cone. This is a much stronger statement, right? In general, it's a very hard problem to say, is there an irreducible cycle representing a given class? And we're able to say yes in sort of a very general circumstance. The classes inside of here, they're actually represented by irreducible moving curves. They're positive in some strong sense. Let me do one more. So here's another theorem. So for this, we need to fix integers. So let's fix k positive integers. Let's fix r positive integers. K1 through kr. And let's suppose that a curve class alpha is represented by a family of irreducible curves such that if you have any collection of general points, so we want k plus 1 general points, r plus 1 general points, say k. So we have xi from I equals 1 to r plus 1 more. Sorry, this sentence is hard to parse. Let me finish it. So suppose that alpha is represented by a family of curves such that for any general points, there is a curve in our family which contains these points. So containing y and containing each xi with multiplicity at least ki. Okay, that's the hypothesis. Then the volume of this curve class, the n minus 1 over n, is at least the sum of the ki's over r to the 1 over n. So if you're an expert in birational geometry, you'll recognize this lemma. This is actually,
You call it a theorem.
Yeah, you'll recognize this theorem. You don't let me get away with anything, do you? You'll recognize this theorem. This is exactly the same thing that shows up when you want to bound the volume of a divisor based on the curves it intersects. So for Sysadry theory, again, or for the boundedness of Sloufanos, this lemma sort of playing an important part. And my point is just that the volume of a curve, this is something which has been studied before, implicitly. Right, and that's not too surprising. If this is really a very natural construction, like I've been trying to, hopefully been motivating, it has appeared sort of implicitly in different times, and this is telling us that somehow, it's giving us a new perspective on this kind of direction, on Sysadry constants, for example. This would allow us to redirect our attention to the curves rather than the divisors, and so hopefully to, be able to make some new progress in those areas. So I'm out of time. Thanks for your attention.
Questions?
So do you think Perron's principle is fake? It's false in higher dimensions or four dimensions?
It should always be true for a complete. So the question is, suppose you have, this idea of Perron, where complete intersections classes are, the mobility is actually calculated by a complete intersection of the class. For complete intersection surfaces and so on, it should be true. I would expect. But of course, when you go up to cycles of higher codimension, there's much more than there's much more than the symmetric product of N1. So there's a lot that you can't sort of handle in this.
The other thing they could be pushed forward is complete interface.
That's right. So, maybe we can talk about this more.
So how much of an evidence do you have for this conjecture start?
Well, I can't calculate a single example. I didn't,
Or how much line you're willing to bet?
except for surfaces.
You mentioned 3, right?
Yeah, I mean, I feel like it should be. This is what I wanted to say. Great, you reminded me. For divisors, this is basically, Serre's theorem about the vanishing of higher cohomology. For divisors, the ample ones are the only ones whose volume we can compute because we have this theory due to Serre. So similarly, you'd hope that complete intersection classes of curves should somehow be the easiest case. I hope that with the right perspective we can make progress, or maybe we should just work with this weighted version.
Is a tropical version of Perrin's conjecture known to be true or false?
I don't know. That's a great question. I've asked some tropical people that I don't think it's known. There's a question in the back.
Yeah, I was wondering, on the Eric Kaloff theory side, what does this suggest and what tools are missing? It seems like a lot of the basic analogs are in place, like volumes and Hilbert-Samuel and logs and cavity.
Yeah. So for Eric Kaloff theory, I'm definitely not an expert, so let me just sort of speculate. This would suggest, first of all, that using convexity to analyze volume functions would be a good idea. And second, we have this sort of invariant we can construct for curves. We should try to understand the relationship with this kind of invariant types of points. Are we actually measuring something via this kind of construction or not? I think those would be two very reasonable goals that you could actually accomplish and see what comes out. For abelian varieties, for example, what this is done.
Any other questions?
For the question, so in the cases Perron studied, these optimal intersection curves, in the known cases, are they all smooth?
Oh, that reminded me of the other thing I wanted to say. Great, this has been very fruitful. So the question was about Perron's study. Are all the curves smooth? I don't know, but it reminded me of something else I did want to say, which is that this conjecture, it's not just coming from nowhere. It's coming from the Gruson-Peskin bounds on genus, right? They're saying that if you have a curve which is not contained in a surface of too small degree, then we know what the we know what the largest genus is. It's for certain ranges, it's computed by complete intersections, but we actually have a very precise answer. Those are also the curves which tend to, morally speaking, high genus should correspond to a large Hilbert, sort of a large component of the Hilbert scheme. So those are also the kinds of curves which tend to maximize mobility.
Sort of this custom normal.
That's right. So that's definitely in there. But the difficulty in sort of following that perspective up is that we don't know how to compute the dimension of the Hilbert scheme based on the G's. That's a very hard problem for space curves. But certainly that picture is sort of, the pictures are compatible in a sense. So this conjecture is not sort of high in the sky.
Any other questions?